Hey friends, welcome to the YouTube channel all about electronics. So in this video, we will learn about the Cascode Amplifier. So we will see that what is Cascode Amplifier, what are the advantages of this amplifier, and then we will derive the equations for the voltage gain and the output impedance of this amplifier. So this Cascode Amplifier is a high gain amplifier, and we will not get such a high voltage gain using the common emitter amplifier or using the any other configuration that we have discussed earlier. So as you know, among the common base, common emitter and the common collector amplifiers, common emitter amplifier provides the highest voltage gain. So if you recall, then the small signal circuit of this common emitter amplifier and the voltage gain can be given as minus Gm times this RC parallel R0, where the R0 is the output impedance of this BJT. So let us put some numbers and let us see the typical value of the voltage gain that can be achieved using the common emitter amplifier. So let's say this VCC is equal to 5 volt and the amplifier circuit is biased with the collector current of 1 milliampere. That means here this IC is equal to 1 milliampere. So if you recall, then this transconductance Gm can be given as this IC divided by Vt. So typically at the room temperature, the value of the Vt or the thermal voltage is equal to 26 millivolt. But here for the simplicity, let's say this Vt is equal to 25 millivolt. That means here this Gm will be equal to this 1 milliampere divided by 25 millivolt, and that is equal to 0.04. Moreover, here let's say the early voltage VA is equal to 50 volt. So from this we can get the value of the R0, because this R0 can be given as this VA divided by IC, and here that will be equal to 50 volt divided by 1 milliampere, that is equal to 50 kilo ohm. And here if you see the value of the RC, then it will not be more than the 2 kilo ohm, because if the value of the RC is more than 2 kilo ohm, then there will be a large voltage drop across this RC, and because of that this amplifier circuit will not operate in the active region. That means here this value of the RC will not be more than the 2 kilo ohm. So let's say that is equal to 2 kilo ohm. So now by putting all these values, if we see the voltage gain, then that is equal to minus 0.04 times these 2 kilo ohm in parallel with 50 kilo ohm. So this value is approximately equal to 2 kilo ohm. So we can say that this VO divided by VI is approximately equal to minus Gm times RC, and that is equal to minus 0.04 times 2 kilo ohm. So that is roughly equal to minus 80. So we can say that the magnitude of the voltage gain for this common emitter amplifier is equal to 80. So as you can see here, if you want to increase the voltage gain, then either we need to increase the value of the RC or we need to increase the value of this transconductance. So as we have seen, if you try to increase the value of the RC, then there will be a more voltage drop across this RC, and because of that the amplifier will move out of the active region. That means here we cannot increase the value of the RC beyond the certain range. So if we cannot increase the value of the RC, then the second thing that we can do is to increase the value of the Gm. So as you know, this Gm can be given as this IC divided by Vt. So if we want to increase this transconductance, then we need to increase the value of the collector current. So once again, if we increase this collector current, then the voltage drop across this resistor will also increase, and hence it is quite possible that the amplifier will move out of the active region. That means here we cannot increase the value of the Gm and the RC beyond the certain limit. So we can say that here the voltage gain that we are getting with the common emitter amplifier with the resistive load configuration is the limited. So here instead of the passive resistive load, if we use the active load such as the current source, then it is possible to get the higher voltage gain. So for that, let us replace this resistive load with the ideal current source. So for the ideal current source, its output impedance will be equal to infinite. So if we see the small signal equivalent circuit, then it will look like this. And here, this voltage gain is equal to minus Gm times R0. So that is the maximum achievable voltage gain with the common emitter amplifier. So this gain is known as the intrinsic gain. So once again, let us put some numbers and let us find out the typical value of this intrinsic gain. So once again, let's assume that this bias current is equal to 1 milliampere. That means here, this collector current is equal to 1 milliampere. And with that, if we see the value of the transconductance, then once again, that will be equal to 0.04. And here, let's assume that this R0 is once again 50 kilo ohm. So with that, if we see the value of the intrinsic gain, then that is equal to 0.04 times 50 kilo ohm, and that is equal to 2000. That means with the given parameters, this is the maximum gain that can be achieved using the common emitter amplifier. But if we see the actual gain, then that will be less than that, because as you know, the actual current source will have some finite output impedance, and because of that, the voltage gain will further reduce. So here, let's say this current source is implemented using the PNP transistor, and let's say its output impedance is equal to R0P. So in this case, if we see the overall voltage gain, then that is equal to Gm times this RON parallel ROP, where the RON is the output impedance of this NPN transistor, while the ROP is the output impedance of this PNP transistor. So for a moment, if we assume that this RON is equal to ROP, then in that case, this voltage gain will become Gm times this R0 divided by 2. So considering the previous values of the Gm and the R0, this voltage gain will be equal to 0.04 times this 50 kilo ohm divided by 2. That means this voltage gain is equal to 1000. So as you can see, with the actual current source, this voltage gain will further reduce from the intrinsic voltage gain. That means if we want to improve the voltage gain of this amplifier, then somehow we need to increase the output impedance of this amplifier. And this cascode amplifier exactly does that. So if you see the cascode amplifier, then it is the cascade connection of the common emitter amplifier and the common base amplifier. So here, this common emitter amplifier is the amplifying transistor. And here, if you see the common base amplifier, then that is the cascode transistor. So as you can see over here, the output of this common emitter amplifier is given as an input to the common base amplifier, and the overall output of the cascode amplifier is taken at the emitter of the second transistor. So here for a time being, this load is not shown in the figure, but this load can be a resistive load or it can be an active load like the current source. But for a time being, let's say there is some load that is connected to this cascode amplifier. So the advantage of this cascode amplifier is that it provides the high voltage gain and the high output resistance. So let's say if R0 is the output impedance of this common emitter stage, then the output impedance of this cascode stage will be the K times R0. And in this way, the output impedance of this cascode amplifier is higher. So here, because of the higher output impedance, if we see the voltage gain of this cascode amplifier, then that will be also higher. So let us understand the same thing using the small signal analysis. And let us derive the expression for the output impedance and the voltage gain for this cascode amplifier. So here, from the DC biasing perspective, this second transistor Q2 is biased with some fixed voltage. But from the AC analysis perspective, this base terminal will get connected to the ground potential. And similarly, this DC voltage source will also get short circuited. So now, let us replace this each transistor Q1 and Q2 by their small signal model. So overall, if we see the small signal equivalent circuit of the cascode amplifier, then it will look like this. So as you can see, here the input is applied between the base and the emitter of the first transistor. And the collector of the first transistor is connected to the emitter of the second transistor. Then here, the base of the second transistor is connected to the ground terminal. And as you can see, here this output voltage is taken across the collector of the second transistor and the ground terminal. So here, this R01 is the output impedance of this Q1 transistor, while the R02 is the output impedance of this second transistor. So with this, now let us find the output impedance of this overall cascode configuration. So now, to find the output impedance of this amplifier, what we will do? We will apply the test voltage Vx at the output, and we will make all the independent sources in the circuit as 0. And in this condition, we will find this current Ix. So the ratio of this Vx and the Ix will give us the output impedance. So here, as soon as we make this Vin as 0, then this Vpi1 will also become 0. And hence, this independent current source GM1 Vpi1 will also become 0. That means now, we will only have this output resistor R01 between the collector and the emitter terminals of the first transistor. And now, if we see the equivalent circuit, then it will look like this. So for the given circuit, now let us find the value of the output impedance. So here, let's say this current is equal to Ix. So here, this current Ix is entering at this node, and the same current will also flow out at this node. That means here, the current that is going away from this node is also equal to Ix. Moreover, if you see, then here this R01 and the Rpi2 are also connected in the parallel connection, because here the one end of both transistors are connected at this node, while the other end is connected to the ground terminal. And here the voltage across both the resistors is equal to Vpi2. So now let us apply the KCL in the given circuit. So if we apply the KCL, then we can write this voltage Vx is equal to Ix minus this Gm2 times Vpi2 times R02, that is this voltage, plus this Ix times this R01 in a parallel with Rpi2. Because here if you see, then the R01 and the Rpi2 are connected in the parallel connection, and the current that is flowing into the equivalent resistance is equal to Ix. So if we see the voltage drop across that, then that is equal to this Ix times the parallel combination of this Rpi1 and the R01. So that is this voltage. So here, if we see this voltage, then that is nothing but the minus Vpi2, because here the positive terminal of the Vpi2 is connected to the ground potential, while the negative terminal is coming at this node. So we can say that this Vpi2 is equal to minus Ix times this R01 parallel Rpi2. So now in the above expression, let us put the value of this Vpi2. So now we can write it as Vx is equal to this Ix times R02 minus Gm2 times Vpi2 times R02. And further, we will also have this Ix times this R01 in parallel with Rpi2. So now, if we put the value of the Vpi2, then further we can write it as this Ix times R02 minus Gm2 times R02 times minus Ix times R01 in parallel with Rpi2 plus this Ix times this R01 in parallel with Rpi2. So further if we simplify it, then we can write it as this Vx is equal to Ix times this R02 plus these R01 in parallel with R by 2 times 1 plus this GM2 times R02. So from this we can say that this Vx divided by Ix, or the output impedance of this cascode stage, is equal to R02 plus 1 plus GM2 times R02 times R01 parallel with R by 2. So here typically this GM2 times R02 will be much greater than the 1. So approximately we can say that this term is equal to GM2 times R02. And further we can write this expression as R02 plus GM2 times R02 times R01 in parallel with R by 2. So once again, let us take this R02 common. That means further we can write it as this R0 is equal to R02 times 1 plus GM2 times this R01 in parallel with R by 2. So once again if you see, then this GM2 times this parallel combination of this R01 parallel R by 2 will be much greater than the 1. So once again, here we can neglect this 1. And further we can write this expression as this R0 is equal to R02 times GM2 times this R01 in parallel with R by 2. So that is the expression of the output impedance. So here as you know, this R by 2 is equal to beta 2 divided by GM2. So typically this R01 is much greater than R by 2. And with that assumption, we can approximately say that this R0 is equal to this GM2 times R02 times R by 2. And here, if you put the value of this R by 2, then we can say that this R0 is equal to this beta 2 times R02, where the R02 is the output impedance of the Q2 transistor. So here, if we assume that this R01 is equal to R02 and the beta 1 is equal to beta 2, then we can say that here this output impedance of this cascode stage is equal to beta times R0. That means suppose if the beta is equal to 100 and the R0 is equal to 50 kilo ohm, then in that case the value of the output impedance is equal to 5 mega ohm. So in this way, using the cascode amplifier, we can improve the output impedance. So now, to find the overall voltage gain, we also need to find the transconductance of the overall amplifier. So what is the transconductance? We have already seen in detail in the earlier videos. So basically, it shows that if the small signal voltage changes by the small amount, then how much change we will get in the output current. So the question is how to find that. So if the Vin is the input to the amplifier and V0 is the output, then to find the transconductance, what we will do? We will find the output current of this circuit. Let's say that is equal to I0. So the ratio of this output current to the input voltage will gives us the transconductance of the amplifier. That means the output current of the amplifier can be given as Gm times Vi. And if we see the output voltage, then this output voltage is equal to minus Gm times Vi times R0. So from this we can say that this V0 divided by Vi, or the voltage gain of this amplifier, is equal to Gm times R0. So we already know the expression of the output impedance. So the only thing that we need to find is the transconductance. And once we get that, then we can find the overall voltage gain of this cascode amplifier. So let us find that. So first of all, this is the small signal equivalent circuit of the cascode amplifier. So here, to find the transconductance, as you have seen, we will connect the output to the ground terminal. And now, we will find the output current in the circuit. So the ratio of this output current to the input voltage will give us the transconductance of this cascode amplifier. So let us find that. So here, once we connect the output to the ground terminal, then here, this RPi2, RO2 and the RO1, all three are connected in the parallel connection. Because if you notice over here, then the one end of these three resistors is connected at this point, while the other end is connected to the ground potential. And moreover, the voltage drop across all the three resistors is equal to Vpi2. So here, if we apply the KCL at this node, then we can say that this I node is equal to this Gm2 times Vpi2 plus Vpi2 divided by R02, because here the voltage across this resistor is equal to Vpi2. That means this current will be equal to Vpi2 divided by R02. And let's say this is the equation number 1. So similarly, now let us apply the KCL at this node. So if we apply the KCL, then we can write this Gm1 times Vpi1, that is this current, that is equal to Gm2 times Vpi2, that is this current, plus Vpi2 divided by R02, that is this current, plus Vpi2 divided by Rpi2, that is this current, plus Vpi2 divided by R01, that is this current. Because here the voltage drop across this RO1 is also equal to Vpi2. So all these currents are the incoming current, while the Gm1 times Vpi1 is the outgoing current. So further if we simplify it, then we can write it as this Gm1 times Vpi1, that is equal to Vpi2 times this Gm2 plus 1 divided by R02 plus 1 divided by R01 plus 1 divided by Rpi2. So here we know that this Rpi2 is equal to beta 2 divided by Gm2. So naturally this 1 divided by Rpi2 is equal to Gm2 divided by beta 2, and definitely it will be less than the Gm2. So we can say that this Gm2 is much greater than 1 divided by Rpi2, and similarly this Gm2 will also be much greater than this 1 divided by RO1 and 1 divided by RO2. That means here we can neglect these three terms, and by neglecting these three terms we can write it as this Gm1 times Vpi1, that is equal to this Gm2 times Vpi2. So let's say this is the equation number 2. So now using the equation number 1 and 2, let us find the ratio of the I0 divided by Vin. So we know that this I0 is equal to Gm2 times Vpi2 plus Vpi2 divided by R02. So here let's take this Vpi2 common. So if we take it out, then further we can write it as this Gm2 plus 1 divided by R02. So once again over here, this Gm2 is much greater than 1 divided by R02, and hence we can say that this I0 is equal to Gm2 times Vpi2. And earlier we have seen that this Gm1 Vpi1 is approximately equal to Gm2 times Vpi2. So from this we can say that this I0 is equal to this Gm1 times Vpi1. And here, as you know, this Vpi1 is nothing but the Vi. So we can say that this I0 is equal to Gm1 times Vi. And from this we can say that this I0 divided by Vi is equal to Gm1. That means the overall transconductance of this cascode amplifier is approximately equal to Gm1. So now the voltage gain of this cascode amplifier is equal to Gm times R0, where the Gm is the transconductance of the cascode amplifier and the R0 is the output impedance of this cascode stage. So as we have seen, this GM is equal to GM1, and earlier we have seen that this R0 is equal to GM2 times R02 times R01 in parallel with R pi 2. So here, for a moment, if we assume that this GM1 is equal to GM2 and the R01 is equal to R02, then this voltage gain can be given as this GM times R0 times GM times this R0 parallel R pi. So typically, the value of this parallel combination will always be less than the R pi. But for a moment, let's assume that this R0 is much greater than R pi. In that case, this R0 parallel R pi will be approximately equal to R pi. So the maximum value of the voltage gain will be equal to Gm times R0 times Gm times R pi. And as you know, this Gm times R pi is nothing but the beta, because we know that this R pi is equal to beta divided by Gm. So from this we can say that the maximum value of the voltage gain is equal to beta times this Gm times R0, and this Gm times R0 is the intrinsic gain of the common emitter stage. So we can say that the maximum value of the voltage gain for this cascode amplifier is equal to beta times A0, where the A0 is the intrinsic gain of the common emitter stage. So as you can see, due to this cascode configuration, the gain and the output impedance of the amplifier increases by the factor of beta. So if we use the same value of the R0 beta and the transconductance Gm, which we have used earlier, then the magnitude of the voltage gain of this cascode amplifier will be equal to 100 times this 0.04 times 50 kilo ohm. That is the value of the Gm and the R0, and that is equal to 100 times 2000. So that is equal to 2 times 10 to the power 5. So as you can see, using the cascode amplifier, the output impedance and the voltage gain of the amplifier will increase substantially. But if we see the actual value of the gain and the output impedance, then that will depend on the load. So if we use the cascode amplifier with the resistive load, then we won't see any improvement in the voltage gain or the output impedance. Because if we use the resistive load, then on the output side, this R0 of the cascode amplifier will come in parallel with the RC. And now this voltage gain is equal to Gm times this R0 in parallel with RC. So typically the value of the RC is much less than R0. So due to that we can say that this voltage gain is equal to Gm times RC, and that is equal to Gm1 times RC. So as you can see, it is same as the voltage gain of the common emitter amplifier. That means if we use the resistive load with the cascode amplifier, then we will not get any improvement in the voltage gain. So to utilize the cascode effect, we need to use the active load such as the current source. So for a moment, if we assume that the connected current source is the ideal current source, then its output impedance will be equal to infinite. And in that case, if we see the small signal equivalent circuit on the output side, then it will look like this. So in this case, this voltage gain will be equal to minus Gm times R0, where the R0 is the output impedance of this cascode amplifier. That means if we use the ideal current source, then in that case, we can get the maximum voltage gain using the cascode amplifier. But as you know, no current source is ideal and it has some finite output impedance. So due to that, the actual voltage gain will always be lesser. So for example, if we use the PNP transistor as the current source, then in that case, let's say its output impedance is equal to R03. So in that case, if we see the voltage gain, then this voltage gain will be equal to minus Gm times this R0 parallel R03. Or if we just consider the magnitude, then that is equal to Gm times R0 parallel R03. So typically, this R0 is much greater than R03. That means the output impedance of the cascode stage is much greater than the output impedance of this PNP transistor. And due to that, we can say that this voltage gain is approximately equal to Gm times R03. That means if we use the PNP transistor as the current source, then in that case, the overall voltage gain is approximately equal to Gm1 times R03. And this gain is almost same as the intrinsic gain of the common emitter amplifier. So as you can see, still it is less than the maximum gain that can be achieved using the cascode amplifier. That means if we want to achieve the voltage gain that is close to the maximum achievable gain using the cascode amplifier, then we also need to use the cascode current stage. So here, this cascode current source is implemented using the 2 PNP transistors. So here, let's say the output impedance of this Q3 transistor is equal to R03, while the output impedance of this Q4 transistor is equal to R04. So here, if we see the output impedance from here, then that will be equal to R04. While if we see the output impedance from this end, then that will be equal to Gm3 times R03 times R04 in parallel with R pi 3. And let's say that is equal to ROP. That is the output impedance of the PNP cascode current source. So now what we can do? We can connect this cascode current source to the cascode amplifier. And if we do that, then this is how it will look like. So here, these two transistors represents the cascode current source, while these two transistors shows the cascode amplifier stage. So now, for the AC analysis, all the DC sources in the circuit will act as a 0. And now, this cascode current source can be replaced by the equivalent output resistance. So from this we can say that the overall voltage gain of this amplifier is equal to Gm times this RON in parallel with ROP, where the RON is the equivalent output impedance which is seen through the NPN cascode amplifier, while the ROP is the output impedance of the PNP cascode current source. So we know that this RON is equal to Gm2 times R0 2 times this RO1 parallel R pi 2, and this ROP is equal to Gm3 times R0 3 times R0 4 in parallel with R pi 3. So the maximum value of the RON is approximately equal to beta 2 times R0 2, because if this RO1 is much greater than R pi 2, then this term is approximately equal to R pi 2, and then this Gm2 times R pi 2 is equal to beta 2. So the maximum value of the RON is equal to beta 2 times R0 2, and likewise the maximum value of the ROP is equal to beta 3 times R0 3. So here typically this RON is more than the ROP, but for a moment let's assume that both are equal. That means this RON is same as the ROP. So when they are connected in the parallel connection, then the overall output resistance will become half. That means now, if we see the overall voltage gain, then that is equal to Gm times this R0 divided by 2. And we know that the transconductance of this cascode stage is equal to Gm1. So we can say that the overall voltage gain will be equal to Gm1 times these beta times R0 divided by 2. And for a moment let's assume that the Gm of all the transistors is also equal to same. So we can say that the overall voltage gain is equal to Gm times R0 times beta divided by 2. And we know that this Gm times R0 is the intrinsic gain of the common emitter amplifier. So we can say that this overall voltage gain is equal to beta times E0 divided by 2. So that is the half of the maximum achievable gain using the cascode amplifier. So for example, if the beta is equal to 100, this Gm is equal to 0.04 and this R0 is equal to 50 kilo ohm, then this voltage gain will become 100 times 0.04 times 50 kilo ohm divided by 2, and that is equal to 10 to the power 5. So still it is higher than the intrinsic gain of the common emitter amplifier. So in this way, using the BJT Cascode Amplifier along with the cascode current source, it is possible to achieve the higher voltage gain. But the only drawback with this configuration is that as there is a drop across each transistor, so the effective voltage that is available to the common emitter stage will get reduced, and hence the voltage swing will also limited. So if we want to increase this voltage swing again, then we need to apply the higher supply voltage, and effectively that will increase the power consumption. So that is the only drawback with this cascode amplifier. But in the applications where we want the higher voltage gain, this configuration is suitable. So I hope in this video you understood how using the cascode amplifier along with the cascode current source, it is possible to achieve the higher voltage gain and the high output impedance. So if you have any question or suggestion, then do let me know here in the comment section below. If you like this video, hit the like button and subscribe to the channel for more such videos.